Hello, this is lesson 1.2a. This is a first part lesson out of two parts. We're going to be talking today about real numbers. So let's get started. I'm going to share my screen with you. Okay, and press present, and here we go. Okay, this is about sets of real numbers. So at the end of this lesson, you should be able to classify real numbers. We've talked about integers, we've talked about whole numbers, we've talked about rational numbers and irrational numbers in the previous 4 lessons, and now we're going to talk about real numbers. And we are going to still be in standard NS1, so by now you should know most of the things from this standard and have at least practiced and tried them out. Knowing that numbers that are not rational are called irrational. Should be able to know that definition. Understand formally that every number has a decimal expansion, and that's converting fractions to decimals. And be able to show that the decimal expansion repeats eventually, and you should be able to convert a decimal expansion which repeats eventually into a rational number. That's the part where we had the repeating decimals from lesson 1.1c, and we turned them into a fraction over a 9, a 99, or a 999. We'll get a chance to practice that a little bit again. Okay, first I have my math meme for you, and I'm going to close myself out here so you can see the full screen. And my math meme for the day, and this should make sense to you, is you've got the number 4 and the pi, and they're in the counselor's office here, and at the bottom it says wife of pi. So 4 is the wife of pi, and she's saying he's irrational, and he goes on and on. She's saying that to the counselor. So that should make sense to you mathematically and should be a little bit funny. Okay, let's move on to the review. I've thrown a lot of stuff at you in the last 4 lessons and new stuff that you may not have had in previous math classes. So it's good to review, and if any of the information that we're reviewing right now is stuff that you're confused on still, I would encourage you to go back and re-watch the videos. The questions that are asked on the videos, the scores are recorded and they will become part of your grade, but you are welcome at any time, as I believe I've said in a previous lesson, to go back and rewatch any of the videos and get a higher score. So let's go on this one. This is the cubed root of 64. What is the cubed root of 64? Remember, it's a number that multiplied by itself 3 times will give you 64 as an answer. This little 3 here is called the index. So what number can I multiply by itself 3 times to give me 64? You can say in your head, 1 times 1 times 1 won't work. 2 times 2 times 2, that will be 8. That's too low. 3 times 3 times 3, that would be 27. That's still too low. But if you do 4 times 4 times 4, you get the answer of 64. So the cubed root of 64 equals 4. Why? Because 4 times 4 times 4 is equal to 64. This one is a square root. How do I know it's a square root? Because the little number 2 usually is not shown in a square root. We just assume it's a 2. That means what number can you multiply by itself twice to give you 144? Think of your doubles in math. 1 times 1, 2 times 2, 3 times 3, 4 times 4. Keep going until you find a double that equals 144. This one, hopefully you know is 12, because 12 times 12 equals 144. Again, I would say it's important to learn your doubles and multiplication up through 15. That would be very helpful for you. Let's do another review question. Write 3 2/3 as a decimal. How do we do that? This would be a great moment to pause the video, work the problem out, and then come back on and watch me work it out and see if you've got the correct answer. So what I'm going to do is I'm going to take 3 times the bottom, so whole number times the bottom plus the top, and make it an improper fraction. So I got 3 times 3 is 9 plus 2. I've got 11, and then it's thirds. It's going to stay thirds on the bottom. And then I'm going to use my long division skills, and I'm going to divide 11 on the top one number on the inside and 3 on the outside. 3 goes into 11 3 times. 3 times 3 is 9. 11 minus 9 is 2. I'm not done. I still have a remainder, so you're going to keep dividing until you realize you have a repeating decimal, or the decimal ends, or there's no pattern that develops over a certain period of decimal places. So let's put a 0 in there, a decimal up here. Let's bring our 0 down. How many 3's go into 20? As close as we can get is 6, right? 3 times 6 is 18. Now we subtract. 20 minus 18 is going to give me 2. I'm not done yet. I still got a remainder, so I'm going to put another 0, and I'm going to bring that one down. And I'm going to say how many 3's go into 20? Well, again, it's going to be 6, and then I multiply 3 times 6. That's going to give me 18, and then I'm going to subtract, and I'm going to get 2. If I were to keep doing this and I put another 0 here, you notice how I'm going to get 20 again, right? So notice we found a spot where we can stop because we have a repeating decimal. So we will put the line over the 6 because we know that it's going to be 6, 6, 6, 6, 6 and repeat forever and ever. We can actually erase the second 6 because the only one that repeats is the 6. So 3.6 repeating is the answer. Let's clear that, and that should be what you got when you pause the video. Make sure you put the little line over the 6. Let's try the other way. This time we have a decimal and we want to write it as a fraction, and the key word here is in lowest terms. So how do we say this number? We say tenths place, hundredths place, thousandths place. So this number is really 4 over 1,000. And that is not in lowest terms. So we have to reduce. We have to find a number that will go in both the top number, the numerator, and the bottom number, the denominator. I know that 4 will go into both the top and 4 will go into the bottom as well. So 4 divided by 4 on top is going to give me 1. 1,000 divided by 4 is going to give me 250. If you don't know that off the top of your head, you could always divide 1,000 in half and then divide it in half again. So the answer then to a fraction for 4 thousandths is 1/250th. Okay, let's go on. Another review. Okay, this is from lesson 1.1c, and this is something, if you're confused on it, you need to go back and watch that lesson again. You can also reach out to me. You're going to change 0.175 repeating into a fraction. I'm using the shortcut method. You can watch the video 1.1c if you would like to see how I derived the shortcut method and how come that works. So step 1 using this method is to move the decimal and the repeating digit to the right, the number of repeating digits, and drop the remaining repeating digits. So I have 3 repeating digits. I'm going to move my decimal 3 places to the right. So there's 2 places. Here is my 3rd place. So my decimal is now going to go right here. So I did that. And I'm going to clear my drawings. And then it says to drop the remaining repeating digits. So I have 175 point, it just would keep going. 175, 175, dot, dot, dot. Cross off the decimal portion. Just keep the whole number. Put your new number over 9 if you have 1 repeating digit. 99 if you have 2 repeating digits, or 999 if you have 3 repeating digits. So since we have 3 digits repeating, I'm going to put 0.175, or in our case 175 now, the whole number, over 999. And then my final step is just going to be to reduce my fraction. Well, I know that 175 over 999 has no common factor that will divide into both the top and the bottom. So I do not have to reduce my fraction. I am finished. I have no reducing necessary. I have just changed 0.175 repeating into a fraction. So that means it is a rational number. It can be written as a fraction. Okay, and the final review question is going to approximate the square root of 8. Remember that non-perfect squares will not have an exact number that multiplies by itself to give you that answer. So there is no number I can multiply by itself to give me exactly 8. I can get very, very close to 8, but I cannot get exactly 8. That is why we have to approximate the square root of 8. This is from lesson 1.1D, and this would be great for you to go back and review as well. So step 1 is to find two consecutive numbers. Those are two numbers that are next to each other that when squared will give you an answer with 8 in between both numbers. So I think of my squares and I try 2 squared equals 4, and the consecutive one after 2 is 3. 3 squared equals 9, and yes, my number 8 will fall between 4 and 9. So the square root of 8 then is going to be between the perfect squares of 2 squared and 3 squared. So I'm going to move that up to the top there. And now step 2 is going to be ask yourself if 8 is closer to the answer to 2 squared or to the answer of 3 squared. So is 8 closer to 4 or is it closer to 9? Well, I'm going to put it my lower limit right there, my 2 squared, which equals 4, and my upper limit, 3 squared equals 9, and I'm going to place the 8 where I think it should go. So my square root of 8 there is going to go closer to the 9. So I know that my answer is closer to the 3 than it is to the 2. And then I'm also going to put in my center number. 8 is closer to 9 than to 4. And I'm going to put my center number in there, 2.5 squared. So where did I get this center number? Well, I added 2 plus 3. So let's do that. I'm going to add 2 plus the 3, and I'm going to get 5. And then to get the middle number, I'm going to divide that 5 by 2. So if I divide by 5 by 2, that's half of 5, right? That gives me my 2.5. So that's halfway between 2 and 3. And then I'm going to square my 2.5, and I'm going to get 6.25. I'm going to multiply 2.5 times itself and get 6.25. I've now created for myself a different lower limit. So we know that the square root of 8 now is between, let me put a red color here, is in between 6.25 and 9. And I have reduced it to no longer being in this half of the quadrant. It is now somewhere between here and there. So let's continue. What's our next step? Find a better estimate using decimal graduation. So we already know that it's going to be in this upper quadrant area here. It's going to be between 2.5 and 3, right? So we are going to try numbers between 2.5 and 3 and square them and see what numbers we get. So we're going to do 2.5 squared, which is 6.25. We have that one already. We're going to try 2.6 squared. That's going to be 6.76. We're going to try 2.7, 2.8 squared, and 2.9 squared. Now we're going to decide where 8 is going to fall between those numbers. So I know that 8, the answer of 8 is going to fall between those two categories. So I know my answer for the square root of 8 that I'm going to approximate is going to be between 2.8 and 2.9. So let's see that come up here. So the square root of 8 is between, and there's that black bar, 2.8 and 2.9. Step 4 is to find an even better estimate. Find an exact, what does that say? Find an exact middle. Okay, so let's look. So we had our 2.8 now is going to be our lower limit. And 2.9 is going to be our upper limit. That's what we decided that the 8 was between. 8 was between 7.84 and 8.41. So now we're going to do the halfway mark in between 2.8 and 2.9. How do I get that? I'm going to add 2.8 and I'm going to add 2.9 and I'm going to add those together. I get 17, carry the 1. I get 5.7. And then I'm going to take 5.7 and divide it by 2. And that will give me my middle number, the exact center between 2.8 and 2.9. So let's put that into our chart here. So 5.7 divided by 2 is going to give me 2.85. So then I'm going to square that, and I'm going to get 8.12. So now I have to ask myself where 8 is going to fall in that. Is 8 going to be on the lower limit here to here? Or is 8 going to be on the upper limit here to there? Where does 8 fall? Is it between 7.84 and 8.12? Or is it between 8.12 and 8.41? Exactly. It's between 2.8 and 2.85. So our square root of 8 now is going to fall between 2.8 and 2.85. So it's going to be somewhere in there. So let's put it maybe right here. So now we have to figure out what number can we use that's close to 2.8 and 2.85, but it's between those two. So let me clear my drawings. So step 5 is to choose your final approximation. So I'm going to pick different numbers between 2.8 and 2.85. So I came up with 2.83 is very close to the square root of 8. So if I take 2.83 and square it, I get 8.0089, which is very, very close to 8. Again, you're never going to get an exact 8 out of that because it's not a perfect square. So 2.83 squared is my final estimate for the square root of 8. Okay, now it's your turn to try a few of those review problems, and I will see you back in a moment. Okay, hopefully you did well on those questions. Let's go into our new content now. What is a rational number? Do you remember? Rational numbers consist of whole numbers, right? Those are the positive counting numbers, 1, 2, 3, 4, 5, 6, 7, etc., etc. And they also consist of integers. Rational numbers consist of integers. Those are the 1, 2, 3, 4, 5, 6, 7, etc. But they're also the negative 1, 2, negative 1, 2, 3, 4, 5, 6, 7, etc. So they include the negative whole numbers as well. And rational numbers also consist of fractions and decimals. They consist of negative fractions, negative decimals, positive decimals. They're all the in-between numbers on the number line. So rational numbers do not include irrational numbers. They do not include irrational numbers. What about irrational numbers? What do they consist of? Irrational numbers consist of non-perfect squares, such as the one we just did, the square root of 8. Remember, perfect squares are numbers like 2 squared equals 4. So 4 is a perfect square. 3 squared equals 9. So 9 is a perfect square. And then you could go on 4 squared, 5 squared, 6 squared. The answers are the perfect squares. So square root of 8, there's nothing I can multiply by itself to give me exactly 8. So it's an irrational number. It doesn't make sense. It's confusing. It will never repeat. It will never terminate. It will go on and on and on. That's what irrational numbers do. Pi is an irrational number. It does not have a pattern. It does not repeat. It never ends. It's irrational. It doesn't make sense. And then Mueller's E is also irrational. You could go on and on with that. Notice how that number there never has a pattern that repeats. It never ends. So it is irrational. Irrational numbers cannot be written as a fraction. They do not repeat and they do not terminate. We're going to take a look at a new term now. Real numbers. What are real numbers? Well, real numbers consist of all types of rational numbers, the whole numbers, the integers, the fractions, and the decimals. And real numbers consist of all types of the irrational numbers as well, the non-perfect squares, the pi's, the Mueller's E. So, real numbers include all numbers except for imaginary numbers. So we will not be in the scope of this class period talking about imaginary numbers, but this is what they look like. An imaginary number is equal to the square root of -1. You can never have a negative number under the square root sign, so that would be an imaginary number. Let's move on. A little bit more about real numbers. So real numbers include, well, there's the imaginary numbers. They're outside of the real numbers. They're not real, they're imaginary. So we're just going to put them outside there so you can see where they belong. So real numbers are going to include the rational numbers and the irrational numbers, right? So what are some rational numbers? Anything that can be written as a fraction. So 27 over 4. That should be 0.333. There should be a point there. That is a rational number because it can be written as a fraction, right? It can be written as 333 over, well, actually it's a repeating 3. 3 over 9. It can be written as 3 over 9, a fraction. 4.5 is a rational number because it's between 4 and 5 on the number line. All the decimals will count for rational numbers. And -6/7, so negative numbers are rational numbers as well. What about irrational numbers? We talked about those. Anything that's not a perfect square, like the square root of 17 is not perfect. Mueller's E. Square root of 2, you can never multiply a number by itself to give you exactly 2. You have to estimate it. Pi, because it never repeats or ends. And the negative of the square root of 11. This is not an imaginary number because the negative sign is outside of the square root. Be careful of that one. So within the rational numbers now, you have subcategories. So within real numbers, you have 2 subcategories of rational numbers and irrational numbers. Within just the rational numbers portion, you have also integers, right? Integers are rational numbers, but they are also integers. So -3, -2, -20, and you could say the positive number counting numbers. Those are all integers. But whole numbers are only the positive counting numbers. They are also integers, but there's only certain ones that are whole numbers. Only the positive values are whole numbers. So 1 and 0 is a whole number as well. How come square root of 4 showed up? Wouldn't you say that's not a whole number? Isn't that weird? Well, it actually is a whole number because the square root of 4 is equal to 2. And 2 is a whole number. So sometimes you'll have to rearrange some of the numbers to classify them. Okay? So we have subsets within subsets. Real numbers include all of these numbers here, all of them. I'll put my little spotlight out. Real numbers include everything except the imaginaries. And rational numbers include all of this. Integers include this, plus this, and whole numbers just include that. So kind of our nice diagram for us. There's 16, another whole number. Okay, let's clear. I'm going to put the chart back up for us as we start to classify some numbers now. Okay, we're going to classify real numbers. We're going to write all the names that apply to this number, square root of 5. What are all the names that apply to this number? So we're going to ask our questions. Is it a whole number? Is square root of 5 a whole number? Well, absolutely not, right? Square root of 5, there's no number you can multiply by itself to give you square root of 5 or to give you exactly 5. So no, it is not a whole number. Is it an integer? Remember, integers are the whole numbers plus the negative whole numbers. So no, it is not a whole number. We decided on the first part, so it can't be an integer either. Is it a rational number? Can you write square root of 5 as a fraction? No, because you're not going to get a number that's exactly precisely going to square together to give you the answer of 5. So no, it is not able to be written as a fraction. Is it an irrational number? Ah, there we go. It is in this category over here of irrational numbers. So yes. And then the last question, is it a real number? Well, irrational numbers are part of the real number category. So yes, it is a real number as well. So we can say that square root of 5 is irrational and real. Okay, let's try another one. Clear my lines there. Put the chart back up there for you to refer to. By the way, this is in your book as well. We're going to classify real numbers. This time we're going to apply all the names to negative 17.84. So is negative 17.84 a whole number? Absolutely not, right? It's a decimal, so it's not a whole number. Is negative 17.84 an integer? Well, an integer is also a whole number, but it's a negative whole number or a positive whole number, and this is not a whole number. Is it a rational number? Could you write 17.84 as a fraction? I would have to say, yes, you could. 17 and 84 over 100, and then you would multiply 17 times 100, and you would get a number that was a fraction. So once I multiply 1700, I multiply 17 times 100, I get 1700, and I add 84 to that, I get 1784 over 100, and that is a fraction. So yes, 17.84 is, or negative 17.84 is a rational number. Let's ask the next one. First, I want to cross off the few that we lost here. It's not a whole number. It's not an integer. It was rational. Is it an irrational number? Is negative 17.84 an irrational number? No, because we said it could be written as a fraction. So that would be a no. And what about, is it a real number? Well, rational numbers are part of the subset of real numbers. So yes, it is a real number. So the answer is, when you classify it, negative 17.84 is rational and real, those two categories. Let's try another one. Put our chart back up there for help. And definitely when you're doing your homework, refer to your chart in your book. So this number we want to classify is the square root of 81 over 9. Square root of 81 over 9 looks like it might be irrational at first glance, but sometimes you have to manipulate numbers a little to see. So we know that the square root of 81 actually has an answer. What is the square root of 81? What number can I multiply by itself to give me 81? Right, 9. So the square root of 81 is really 9, and then we still have this 9 on the bottom. But what is 9 over 9 equal to? A number over itself is always equal to 1. Right? So now the square root of 81 over 9 is really 1. So now let's ask our questions now that we've manipulated our number. Is it a whole number? Is 1 a whole number? Yeah, absolutely. 1 is a whole number. So yes, it is a whole number. Is it an integer? Well, if it's a whole number, it has to be an integer because the whole numbers are inside of the integer category. So yes, it's an integer. Is it a rational number? Well, if it's a whole number and an integer and it's all inside of the rational number box, it is also a rational number. It can be written as a fraction, 9 over 9 or 1 over 1. Is it an irrational number? No, because we've already said that it could be written as a fraction, so it is not irrational. And finally, is it a real number? Of course, it is a real number because real numbers are all the numbers, right? So this one has 4 categories. Square root of 81 over 9 is a whole number, an integer, a rational number, and a real number. So remember, you may have to manipulate the numbers. Okay, now try one more example here before you get to try. -10. Is it a whole number? Remember, whole numbers are only the positive counting numbers. 1, 2, 3, 4, 5, going from the right of 0 on the number line. So no, it is not a whole number. Is it an integer? And integers are the positive and negative whole numbers. So yes, -10 is a whole number and it's an integer. It's a negative whole number, I should say. Is it a rational number? Of course, rational numbers include the integers. Is it an irrational number? No, it cannot be both rational and irrational at the same time. And -10 can be written as a fraction of -10 over the number 1. Finally, is it a real number? Of course, because it is a rational number, it is also real. So the answer to -10 is, it is an integer, it is a rational number, and it is a real number. Now, clear my screen here. It is your turn to give classifying real numbers a chance. See you back in a moment. Okay, welcome back. Hopefully you did well on those questions. Remember, you can always rewatch the video and try again if you would like. Just want to talk about a little bit of higher order thinking. So let's decide if the statements below are true or if they are false. So number 1 statement is all irrational numbers are real numbers. So think about our categories. Real numbers include both irrational and rational numbers. So are all irrational numbers real? You should have said true to that. Every irrational number is included in the set of real numbers. Number 2, no rational numbers are whole numbers. No rational numbers are whole numbers. Think about that category on the left of our chart that was rational numbers. It had 2 circles inside of it, right? It included integers and it included whole numbers, right? So this statement is false. A whole number is a subset of rational numbers. It was one of the circles inside under the rational numbers box. Number 3, all rational numbers are integers. Are all rational numbers integers? Are all rational numbers negative whole numbers or positive whole numbers? False, right? Every integer is a rational number, but not every rational number is an integer. Think of 3/5. That's a rational number, but it's not an integer. So you got to keep those in mind when you're thinking through those. Now you get to try a couple true-false questions. Okay, I'm going to bring myself back here. Hopefully, there I am. Okay, so your homework is going to be doing page 18, numbers 1 through 10, and page 19, numbers 14 through 19. And remember, you may have to manipulate some numbers when you are classifying them. So I hope you have a great day. That's the end of the lesson. We will see you in the next lesson. Bye.